Good morning, students. Dr. Arvind Sharma, Associate Professor in Physics, Government Nagar College, BIKANER. Welcome all of you. Today, our topic is why quantum mechanics. What is the necessity of quantum mechanics? Why quantum mechanics? Then you think about a very deep subject because you all are studying quantum mechanics in BSc Part 3rd, and quantum mechanics is a very deep subject. That means this subject have such kind of concepts that are not easily understandable by everyone, and if you want to understand these, then in your mind, according to their physical picture should be clear. That means your conceptual picture is related with some physical picture or some natural phenomena, then you can understand easily. So this topic is very large, but we just try to confine it according to your class. I just taught you few things, and I suggest you that you read any article on this topic that can enrich your concept in this field. So let us start. Why quantum mechanics? First of all, why is quantum mechanics important? Quantum mechanics is important because it plays a fundamental role in explaining how the world works. How the world works. Just see this point. Physicists often say quantum mechanics governs the behavior of microscopic systems. Microscopic systems, when in fact it governs the behavior of all physical systems, regardless of their size. That means it is for every kind of size, that means micro and macro. And quantum mechanics is also important for the theory of computation. So it is a very important concept that quantum mechanics plays the role for both kind of systems, micro and macro, but it is observable in microscopic system. So normally the idea becomes in your picture that quantum mechanics is for small systems, but it is not true. So just review this thing. Second question, what is the difference between quantum mechanics and quantum physics? What is the difference between quantum mechanics and quantum physics? Very unexpected question, because at present today there is no difference. There is no difference because we commonly use quantum mechanics or quantum physics. But the quantum in quantum physics comes from quantum mechanics. Quantum in quantum physics comes from quantum mechanics, whether it is relativistic quantum physics or non-relativistic quantum. Relativistic and non-relativistic. The difference between the two is only of historical interest. Within a few years, it was replaced by Heisenberg and Schrodinger's quantum mechanics. Heisenberg and Schrodinger's quantum mechanics. Next, what is quantum mechanics? That is very important. What is quantum mechanics? Quantum mechanics is a science of branch, that means branch of science or branch of physics dealing with the behavior of matter and light on the atomic and subatomic scales. Atomic and subatomic scales, that means small particles. It attempts to describe and account for the properties of molecules and atoms and their constituents. Their constituents: electrons, protons, neutrons, and point to be noted that and other more esoteric particles such as quarks and gluons. You are familiar with these terms because you study these terms in nuclear physics. If some student left for choice such kind of things, then you can easily understand when you read the chapter elementary particles in nuclear physics. What are quarks? Normally every student or and simple science student know about that electrons, protons, neutrons are the smallest quantity and they are not built from any other particles. But electrons and protons and neutrons are also made from some other particles, that means small entity, that is known as quarks. And gluons is a quite different elementary particle. There are four kinds of interactions, and you all know electromagnetic, gravitational, weak, and strong. So in electromagnetics, there are many particles that you use. So just go through. Now, these properties include the interaction of the particle with one another and with electromagnetic radiation. These properties include the interaction of particles with one another. Particles का interaction जो है, interaction of the particles or with electromagnetic radiation, like as light, X-ray, and gamma rays are the examples of electromagnetic radiations. Another way, it results in what may appear to be some very strange conclusions about the physical world. At the scale of atoms and electrons, many of the equations of classical mechanics, which describes how things move at everyday size and speeds, cease to be useful. In classical mechanics, objects exist in a specific place at a specific time. In classical mechanics, objects exist in a specific place and at a specific time. However, in quantum mechanics, objects instead exist in a haze of probability. You all know about the probabilistic interpretation of the wave function, which is directly proportional, or which is directly concluded that it depends upon the Position of the particle. So, position of the particle is probabilistic. They have a certain chance of being at a point, another chance of being a different point, and so on. It may be point A, B, or you can say 1 point, second point, or third point. So, what we understand from it that quantum mechanics is a new physics which explain the physical systems according to probabilistic interpretation. Now, these are very basic questions which arise in your mind. So, just I try to incorporate the things in question answer form that you can easily understand, and they are also useful for your examination point of view. Question number 4. Which are the revolutionary principles of quantum mechanics? Which are the revolutionary principles? That means how many principles that are responsible for that kind of revolution that we go from classical mechanics to quantum mechanics. And these all things you study and all you familiar from these concepts. First concept is quantized property. First concept is quantized properties. Before that, quantum mechanics developed over many decades, beginning as a set of controversial mathematical explanation of experiments that the math of classical mechanics could not explain. Maths and concepts in the beginning, at the turn of 20th century, there are many kinds of experiments like as photoelectric effect, Compton effect, and first experiment is all of you familiar, black body radiation spectral distribution curve. So there are many experiments which cannot be explained by the classical mechanics, and there are few scientists like Max Planck, Albert Einstein, and different scientists who explains these properties, these experimental results and concepts by their new fundamental ideas. So what is our theme? That revolutionary principles of quantum mechanics. First is quantized properties. You all know that quantization concept given by Planck and also Einstein. There is a very big difference. Planck says that emission and absorption of the wave or propagation of the wave in the space. There are two things. Planck says that emission and absorption is a discrete process, that means like particle nature. But wave propagates in the space like as a wave. But Einstein changed this idea that both times in quantum mechanics or quantum mechanical arguments, emission and absorption of light as particle, that means quantized nature, and it also propagates in the space as particle nature. So it is explained here. You can easily read this article. I upload this article in your WhatsApp group. What is the help from these arguments? Quantization help to explain other mysteries of physics. Einstein used Planck's hypothesis of quantization to explain why the temperature of a solid changed by different amounts if you put the same amount of heat into the material but change the starting temperature. Similarly, in spectroscopy, spectral lines. In spectroscopy, spectral lines are explained by the Bohr's theory. What Bohr proposed? Bohr proposed that electrons were restricted to special orbits around an atom nucleus, atom's nucleus. They could jump between special orbits, and the energy produced by the jump caused specific colors of light observed by spectral lines. When electrons jump from one state to second state, then they emit light, and these are observed as spectral lines. Though quantized properties were invented as but mere mathematical trick, they explain so much they become the founding principle of quantum mechanics. Second one is particles of light. First is quantized properties. Second one is particles of light. In particles of light, there are many things are explained here. You just read it and try to understand. I just explain you some few major things. What Einstein explained when he published his paper concerning an heuristic point of view toward the emission and transmission of light. Emission and transmission of light. He explained that light traveling not as a wave, but as some manner of energy quanta. Energy quanta, and this packet of energy Einstein suggested could be absorbed or generated only as a whole. That means energy of quanta, you know that minimum energy is known as photon energy, that is not breakable. If photon is absorbed or emitted, and you know E equal to hν or E equal to nhν, where n is a number, so it cannot be break. So these things are explained here. We all are familiar because you also study in your class BSc third year in quantum mechanics. We easily understand these things. Here, with this new way of envision light, Einstein offered insights into a behavior of 9 different phenomena. 9 different phenomena. There are many phenomena here try to explain, including the specific color that Planck described being emitted from light bulb filament. It also explained how certain colors of light could eject electrons of metal surfaces, a phenomena known as photoelectric effect. Photoelectric effect. Einstein also winning Nobel Prize in 1921 when he explained experimental results of photoelectric effect. His discovery of the law of photoelectric effect. After that, Einstein also published a paper termed phonon. You just read it. So, it is clear that light could behave both as a wave and a particle. That means wave particle duality. Last, that means third revolutionary principle is waves of matter. Waves of matter. That means matter waves. That concept is given by, you all know that this was given by de Broglie, because before de Broglie, light behaves like a wave. In many experiments, you see that not many, in every experiment, matter is behave like a wave. But de Broglie says that if a particle moves, if a particle moves with some velocity, suppose you have a particle of mass m and it is moving with velocity v, then a wave is associated with it. That is known as matter wave. Initially only a single wave considered, but when some physical arguments try to explain this thing, that this is not physically acceptable, and after that a group of waves, that means wave packet, considered associated with the particle. Physically, wave packet is associated with the wave, and physically it is proved. So you can easily understand all these things which I include in this lecture. So I also upload this text in your WhatsApp group. You know, after that Schrodinger, after de Broglie, there are many scientists like Heisenberg, uncertainty principle, Max Born, physical interpretation of wave function, Schrodinger, Erwin Schrodinger. Schrodinger is the main scientist who play the key role in quantum mechanics. And Heisenberg, Schrodinger gives the model of atom. What they say, that each electron acts as a wave, sometimes referred to a cloud around the nucleus of an atom, replace the Rutherford Bohr model. Heisenberg-Schrodinger model of atom, electrons obey a wave function and occupy orbitals rather than orbits. Unlike the circular orbits of the Rutherford Bohr model, atomic orbitals have a variety of shapes ranging from sphere to dumbbells to daisies. Spheres to dumbbells to daisies. Different geometry of the orbitals. So physics is not so easy to understand. It's very hard when we try to understand the concepts. So this first lecture, you don't afraid about that physics is very hard, because that is only beginning of your M.Sc. physics. There are maths also when we go through next lectures. Here I just try to explain the things, because you are already study quantum mechanics in your BSc third year classes. So don't bother about that. Don't bother about that. How much things you understand, you try to understand, try to read and try to understand. If something is you not understand, then you continue your study, and after some time again read such kind of articles that you are not understanding well. Because in physics and in science, it's not necessary that at the first time you understand all things. After, other than these things, you all know about the uncertainty principle. That is also a very good concept by Heisenberg, and different things also that is not in your course yet. These are higher classes topics, that is quantum field theory, quantum electrodynamics, electroweak theory, quantum chromodynamics. That means quantum mechanics is a very vast topic, and in higher classes or in research areas, it have many kinds of applications in every branch of physics. Thank you, students. Thanks.